All right, so hey everyone, and welcome to this seminar. So today we have the pleasure to welcome Andrea Maselli from the Gran Sasso Science Institute. And Andrea will talk about probing vacuum general relativity, where to look and what to seek. So thanks, Andrea, for being here, for giving this seminar. And you have the floor. If anyone has questions, feel free to ask, and we have time at the end too.
Okay, thanks a lot. It's customary to say thank you for the hospitality, but I mean, this time I really have to do it because I mean, this month here was just fantastic. I mean, thanks for everyone for welcoming in here. Sorry that Miguel is not here because I mean, took care of everything. Also, the staff at the secretary that basically helped me a lot. And thanks for all the experiences. I mean, for people that haven't done this, I mean. This is a canteen, like the Porto Reset Factory, where they do a particular variety of Porto in Portugal. This was a fantastic experience, and that made everything even more than scientifically oriented. So, what I'm going to talk today, so I think I slightly changed during this month a bit my focus, and I won't be very, very specific. I hope that in these 2 days that we still have, if you find something interesting, you can chat with me. What I actually want to give you also because I believe that the group, I mean, really in this moment doesn't work on this particular topic. Here, I want to give you a bit an overview of what has been done in this field that has been actually heavily Portuguesized in the last period. There have been many Portuguese people giving contribution to this field of probing vacuum general relativity, and I actually want to give you an idea of where things, what's the kind of fundamental physics or astrophysics that we can do, and I'll then focus on some specific things that I've done with collaborators and with students. So, what are environmental effects? I think that there is a sort of clear case that we can do with the gravitational waves and next generation detectors. It's not clear whether we can do it in the sense that we can extract meaningful information, but at least there are things that are there which are astrophysical environment. And so current or standard modeling of gravitational sources is done in vacuum, but of course, I mean, we know that it's not true because black hole basically don't live and evolve in isolation. There is a multitude of field gas that goes around. There are open problems where basically, which could be dark matter or so it's formation and the features. And we know that basically we have seen objects that evolve in astrophysical environments, massive black holes that coalesce in dark matter halo. You have IGNs, so basically surrounded by accretion disks. There are stellar clusters. So actually, one of the binaries that we observed with LIGO Virgo is thought to merge in the accretion disk of a massive component. So there is stuff there which definitely is non-vacuum. Now, this basically, when you have this thing, you basically have 2 roads which are complementary. One is trying to understand whether basically you can actually exploit this astrophysical environment to get insight, fundamental astrophysics insight, the density, or the property of the dark matter, the viscosity of the accretion disk, the interaction of stellar clusters, so on and so forth. The other is basically arguing what are actually measuring. In the sense, if we have vacuum templates that we are using to study things which are non-vacuum, are we actually getting the real parameters of the binaries of masses and spin, or are there contaminations? Now, the wheel of environmental effects that have been studied, I mean, is incredibly large. I just, what I want to show you in the next slides are basically some cases of these, and in particular, how physical effects relate to different physical science, like cases here, how they pinpoint, how they arise, or how they leave signature in the gravitational wave emitted by sources. And when I talk about sources, I think it's very important that in general, it's not only environmental effects, but if you talk about fundamental physics, so even testing exotic compact object or beyond GR, I guess that this is basically the realm of next generation detector. Okay, LIGO and Virgo are not really precision physics instruments. And when we're doing with the next generation detectors, basically we're going to have different sources compared to only those that we've observed so far. We have what I call a bit the boring comparable mass binaries that there are now more than 200 in the gravitational catalog. But in the next future, we'll also observe what I call asymmetric binaries, so like extreme and intermediate mass spatial spirals, in which there is, say, a very massive black hole at the center and then a stellar mass object going around. I'll give you more information, but this is a different kind of source that we have not observed so far. You cannot actually observe these sources with light and Virgo because they emit signals in the milliards band, so out of the current band. And the problem is that the way that mathematically you describe this and this is very different. So you need to think about how to, and it's not only like the variety of environmental effects, but the variety of sources that will force you to basically find a bridge between the different modeling, the different effects, the way that they pop up. And this is actually what I want to show you today. So let me give you basically a practical way to understand how environmental effects enter and where do we look for signatures. So basically, you have the binary, which are classical binary, either like symmetric or asymmetric binary that basically evolve in some non-vacuum environment. And the fact that there is something there will basically change the generation and propagation of gravitational waves. So if you have the standard way of describing the phase of the signal, you basically have your vacuum contribution plus something which deviates from vacuum. And actually there is, in the majority of times, the majority of effects, you can actually write this environmental effect as a deformation of your vacuum model. And this deformation, which depends parametrically on some parameters like the density of the environment, actually can be mapped on different effects. For example, here, this parameter gamma that enters this shift in the phase can actually describe 3 different physical effects that you can have from a non-vacuum environment, like accretion of matter on the black hole, or you have gravitational pull, or what is called gravitational drag. You may actually have heard about this as dynamical friction. Okay? So basically the fact that there is a black hole going around in some matter, and this matter is actually slowing down the black hole because it's exerting, if you see, a pull. So basically the black hole is going in this direction, and it first like this, and then it creates a wake on its behind, and this wake basically attracts the black hole, so slow down its motion. Okay? So can we use basically this kind of stuff? Yes.
So this gravitational drag, I would assume that it depends on the density of the medium.
Yeah.
But here I would see 11/3. That seems to be independent.
No, the density is encoded here in this particular thing here.
I see.
And I think this is also, I don't remember, this is actually a particular simplified form, which, if I remember correctly, this is for collision-less dynamical friction, so the Chandrasekhar, basically the Chandrasekhar formula. But in a more general format, you would have basically here something that would encode different properties of the medium, so for example, viscosity or other stuff.
But the exponent doesn't depend on the density. That's is that an assumption, or?
No, you can actually show that basically, because I mean, this corresponds to a particular force acting on the binary. Force means 1/r some exponent. Then you can map this in a post-Newtonian way such basically to show these exactly this behavior here for all types of, at least for mass, so for particles. Yeah. So the exponent will be there, and then you will probably have here like a more complex coefficient which takes into account basically the overall properties of the medium.
Right. And this hierarchy that you see here, so 11/3, which is a bit larger than 3, a bit larger than 2. You know, I would have assumed that, again, I mean, just qualitatively, so there's a stronger effect from the gravitational drag versus accretion versus gravitational pull.
I'll come in the next slide to this.
You'll come to that.
Yes.
But I would assume that, again, if there's gravitational, there's some assumption. Gravitational pull, it will depend on the distance as well.
Yeah, absolutely. But this is actually encoded here as well. I mean, the exponent basically carries like the frequency content of the evolution, so basically tells you whether this is more active when you are far or closer, basically.
Because the frequency will increase.
Exactly.
But then, yeah, it's still more important, the gravitational drag than the gravitational
Absolutely, absolutely. No, I just put here to show up different contribution. But indeed, drag, you are anticipating my next slide, which is this one, and indeed, drag is actually the best constraint parameter in general. And in this figure here, actually, I want to show you how these effects are measured and which are the binaries that actually are the best one for offset but constraining environmental effects. So actually, as Carlos was noticing, there is a hierarchy, and let me actually point out something, that basically this minus here pops up or actually highlights that environmental effects come from or actually show up in the waveform of what are called negative post-Newtonian orders. So basically, if you study basically the way that we emit that in vacuum general relativity, the gravitational wave signal is described, well, the leading order is the quadrupolar, okay, effect, one that you study during the course, and then, which is basically the weak field expansion of your equation is the leading order, and then you can add to this to increase the accuracy of your model positive terms, which are positive, are known as positive post-Newtonian order. So basically, if I can go 1 second to the blackboard. Basically, you will have the quadruple term here, and then you will have other terms, which basically goes as v over c to n. The c is the speed of light, v is the characteristic velocity of the binary. Okay. In vacuum general relativity, there are no pre-Newtonian terms. So basically, terms which basically come, these are basically with n larger than 0. Okay. There are no negative terms. Okay. But environmental effects actually tend to be very, very negative. And indeed, the dynamical friction that Carlos was actually mentioning is minus 5.5 pm. So the Q is 0, minus 5.5 is something which basically is very, without very, very general, very specific, like this, very, very negative pm. Now, what does it mean, this? That if you basically have this waveform construction, okay, basically, the hierarchy of the post-Newtonian order corresponds also to the range of frequencies in which the effect is active. And if I could draw a line of the frequency, this is basically high frequency, this is basically low frequency. So basically, terms which are very positive contribute at high frequency, terms which are very negative contributes at low frequencies. Okay. This is, for example, the merger, okay, where you need a lot of high positive terms to make a faithful description of the signal. And you can see this actually, because, so take this, which is gravitational drag, so dynamical friction. In this work that we did with Vitor, we basically try to see which is the smallest density that you can actually measure depending on the source, and I'll actually tell you which sources are these. So these are just 3 prototype LIGO Virgo binary, like the first event, GB150917, the binary neutron star and another that I don't remember. But then look at this plot. These are like massive black hole binaries in LISA. Okay. These are the constraints for different detectors. So on the smallest density that you can measure, normalized by the density of water. I don't know why Vitor was obsessed to normalize this to water. But you see basically different binaries of the massive black hole. And then you see EMRIs, these asymmetric binaries that I was telling you, 10 to 6 tensor mass, or an IMRI, okay, 10 to 4 tensor masses. And you see that actually the EMRI and the IMRI do actually the best job in constraining these parameters, even several order of magnitudes better than the massive black hole binaries. Now you may think, okay, what's special in this? What's the real novelty? Is that if you basically compute the signal-to-noise ratio, so the loudness of these and these, they are separated of order of magnitudes. So these are expected to be the loudest signals in the universe, while these basically have signal-to-noise ratio which are even lower than or are comparable to those that we observe now in Large Virgo with the stellar mass binaries. Say, these have 500 up to 1000 signal-to-noise ratio. This is at very best of 100. What makes the difference is that this thing here evolved at low frequency for a lot of time, and so these effects, which are the environmental effects, which are very, very negative, have a lot of time to show up and accumulate during the signal. Just to give you an idea of what, because I'm going to focus mostly on this extreme mass Ricci spiral, basically this extreme mass Ricci spiral, again, this stellar mass object that is going around a more massive guy. This is the mass ratio, so basically it's between 10 to minus 7 and 10 to minus 2. Think about that at the very best, I believe that in the current signals that I've seen has a mass ratio of the order 0.1. So here we're going to 10 to minus 6, 10 to minus 7. And they do a lot of orbits, 10 to 5, 10 to 6 in 1 year of observation. Like I think the first event that we observed with Large Virgo, I think did 2-3 orbits, order 10 basically. So this is an insane amount of orbits, and then they're going to be observed from months to years by LISA, and they basically follow rich trajectories. on inclined and eccentric orbits, which is something that really don't show up in the binaries that we have now, which are vanilla, equatorial, and circular orbit. This is basically one of the video that shows the complexity of these orbits. Here, you can see this is a patch of the evolution of an M-ray random access black hole. So yes, so just to conclude, basically richness of the trajectories, orbits, and long evolution makes very, very good for any fundamental physics. Yes.
Just a quick question. So with what was computed that trajectory, is it for Newtonian or is it?
No, this is self-force theory. I guess the leading order is self-force, so perturbation theory in a mass station. Yeah.
Kind of perhaps jumping a little bit ahead, but I was wondering if this conclusion is optimistic, the one that one can constrain better these environmental effects with the others, because at the end we will not see one M, we will see a lot of them. So adding to the difficulty, we have the statistics of that.
Yeah, yeah.
So maybe we'll comment that afterwards, or you can say a few words now.
I absolutely have no idea. In the sense that I know, so yeah, you're referring to the global fit in general. Yes. So this is basically in any, so because the key difference with respect to LIGO and Virgo is that LISA will observe everything together. And when I say everything, means this and actually the louder signal, so the massive black holes, blah, blah, blah. If I understood, I'm not an expert on this, how they're going to do that analysis, they're first basically going to subtract all the very loud signals, so say the more massive. Everything left will be probably like these extreme mass spirals, and then in any case you have to do like an enchilada analysis on those things. I think, so now that I think about it, probably they're going to do it because environmental effects, I'm actually going really forward in the talk, are not probably contaminating their small effects. So I'm not expecting them to bias the measurements of the intrinsic parameters of the masses and the speeds, which are actually those that allow you to catch the signal in the waveform, in the noise. Okay. So as I see it, probably people will catch the signals and then in post-processing analyze them with templates augmented in order to have beyond GR or environmental correction. Because in any case, this kind of, even unless you have like some macroscopic variations from GR, like in this case, both beyond GR expected and environmental effects, there's not going to be huge bias in the intrinsic parameters. So this basically means that probably people can actually search for entries with their backing templates, get the mass and the spins, and get the waveform out of the stream, and then you post-processing basically you come with your model and you analyze it. I think this is the best answer that I can give you.
Right. I was kind of well, we can discuss afterwards, but the overall answer that is.
Okay, and now let me go to like some actually more physical scenario. And what I want to discuss a bit is something that actually worked in the last years, which is basically dark matter spikes, which actually shows you a concrete example of how we can use these binaries, not only M-rays, basically to constrain environmental effects. So some years ago, actually, there is like the two seminal series of papers by Gondor and Joseph Silk, and then by Clifford Wheatle and collaborators, basically studied what happens when you have a black hole in a reservoir of dark matter. These black holes accretes, and basically what it does in accreting is creates an overdensity, so a spike. So basically these dark matter particles rearrange themselves such that there is an overdensity close basically to the black hole. The length scale of the overdensity is dictated basically by the mass of the black hole. There is a particular way to compute the profile that from flat gets basically this peak close to the black hole. And this is actually very, very good because, okay, environmental effects are very, very small. And if you take dark matter, at least at the level of massive particles, not ultralight fields, it's going to be very, very difficult to measure them if there aren't processes like these dark matter spikes that increase the density from what, I don't know, say the solar network value that we already have constraints. So basically, this overdensity here, which is actually also and I'll show you a plot, in the domain where actually extreme mass energy spirals are expected to merge, will push up a lot the density of dark matter, possibly giving rise to detectable signature. Now, actually, when you have a black hole surrounded by this peak, you can have an extreme or intermediate mass energy spiral, but you can also have like a comparable mass binary, and we have two black holes, each of them with their own spike. This is a bit less favorable scenario, at least in the, if you believe that, I mean, for model of dark matter particles which are heavy, the Webb case, and this is because this profile will tend to be depleted or disrupted by repeated mergers or basically other encounter of black holes with objects of the similar size. Okay, so in general, it is assumed that only these asymmetric binaries, where there is a little perturbation that will not damage too much during the process, the spike will actually survive and will provide detectable signal. Okay. So the question is, can we use this, which is a physical scenario, to detect, to get information on the density? So just to give you like a more practical guide of what's happening, basically, when I'm talking about these spikes, it basically means that, think about this step-by-step process in which you have a dark matter with some density here, you plug a black hole into this dark matter density, and at the end you basically get a density with basically has a radial dependence with basically this gamma, which is larger than the original one. So basically your profile has stiffened because the black hole has started accreting matter. Okay, and this is basically indeed the blue line. This is basically the peak that is formed after the accretion. And this is basically the radial distance with respect to the black hole. And this blue zone corresponds basically to the typical orbital range in which an extreme mass energy spirals would merge into LISA in 4 years. So basically the peak is right there where extreme mass energy spiral will actually coalesce. Okay. This is actually also recently people, all this business has been done mostly for Schwarzschild black hole dark matter, but from the seminal work of Clifford Will, then Emanuele Berti and his group and Mississippi have actually completely have analyzed more in detail the effect of having rotating black holes accreting dark matter, and you see actually that the spin increase also the stiffness and of the spike. Yes.
Observationally, is there anything known about this?
Not very positive, I would say, because I mean, from like this motion of stars, like I think around Sagittarius A star. I mean, it also comes to the question whether these peaks are really universal, but it seems that at least in the orbit of this S2 star, I guess, there's less than 1,000 basically solar masses, which basically means that if the peak is there, it may, depending on the model, it maybe is not as big as basically this simple or naive expectations basically suggest. So there will be something more shallow, basically, or something which is flat and another. Again, all of these basically, I guess that this is actually the project that we are now doing with Miguel. The basic idea, the problem is that you will not expect that the spike survives completely unaffected with all the processes that this massive black hole basically is having. I mean, you throw thousands of basically mergers, I mean, things will be distributed. The point is the time scale in which the black hole reacts matter. If the spike is informed, then it's an open problem. You can actually, but from again this observation of massive black hole, you can actually basically already see that if there is a peak, it's probably shallower than basically just predicted by this original formulation.
And in these models, typically, what's the percentage of mass that's in the spike or the dark matter, the post-black holes compared to the black hole mass? Is it like very, very tiny? Or
but maximum in the spike, so the order of 0.1 parsec, more or less, should be, if I'm not wrong, one so of the mass comparable to the black hole.
mass comparable
Yeah.
to what?
Yeah. Which in any case, I mean, it's smaller compared to the halo. I mean, we're talking, I guess, the Milky Way, we're talking 10 to 6, or Sagittarius A star, 10 to 6, 10 to 12, the halo, the halo, and so the spike is there is going to be another solar mass. And another 10 to 6 solar masses.
I see. but not that close.
Basically, the outer boundary should be so. This depends a bit on the particle, but basically it should be around 0.1 the radius of gravitational interaction of the dark matter particle. So if you have a dark matter particle with like some dispersion velocity sigma, basically the gravitation, the radius of gravitational interaction of the black hole will basically just given by this. And the outer boundary of the spike should be 0.1, this number here, should be around, I guess, 0.11 parsec, more or less. Or a typical value of, say, 100 kilometers per second of sigma and 10 to 6 solar masses.
So to be concrete, so in the case of Sagittarius stars, since we have S2 star at about 1,000 Schwarzschild radii, how much mass compared to the mass of the black hole should be there? For I don't know if you're going to talk, but because there are constraints, I was discussing. There are some constraints even for closer. You know, they have these bursts, and they claim that they can say something, and that essentially the 4 million times 10 to the 6 is within a few, the Schwarzschild radii, not 1,000, which would mean that.
I can give you the numbers later on. I think within the orbit of S2, there is basically, again, this probably I don't know more, probably less than 10 to 3 solar masses, 1,000 solar masses, as measured by the gravity experiment.
Yeah, exactly.
And so then, given a model for this big, you can actually, which basically has this dependence on the range and gamma, I can actually tell you in the orbit of Sagittarius how much would be in the spike, mass of the spike, given actually the constraint, which again is not, I don't know, I need to look up the number. I can tell you later, but I can tell you already that it's not going to be this spike. I mean, it's going to be longer.
So, related to this, so it is right, or at least I have heard that the models with ultralight scalars tend to produce flatter profiles. So this mass content that is measured for the Sagittarius star is consistent with these models, or is it also too low for those models?
Good question. I don't know. I should have looked at the numbers. Yeah, I have a slide on the ultralight fields, which and then indeed, I mean, will actually produce over density, but I mean, they are different from this because the Broglie wavelength is basically comparable to the. So, but it's yeah, I don't have the numbers. I should come. Give me this afternoon, probably, then I'll come up with the.
That's okay. It is just curiosity.
No, it's actually important.
If you actually look at these quasi-bound states, I mean, there's a clear spike. I mean, so for Schwarzschild, they will see this, but it depends on the mass. Fundamentally on the mass, and if you put the mass very, very small,
and at this point, actually, then you have interactions. And on interactions.
That's right. So I was thinking about the simplest model without self-interactions, but that will depend on that. And this is all linear. So people have done, Mexican people have done this non-linear kind of analysis, which changes a little bit the distribution as well.
Okay, so I already apologize in advance because I have a slide on this, so I haven't decided the next year. So let me give you a possibility of how to describe in an ab initio calculation the evolution of Emery and Imrichs in this kind of setup. And this was the work that, again, was well, I've done part of the Portuguese society, so I would say that I was within the ballpark of Portuguese people here doing this. So what we did here was basically to try to have a model of black holes, a relativistic model of black holes surrounded by matter, and we went for the easy way, so the spherical distribution of matter. That then, I mean, we assign the profiles such to describe the dark matter profile. So basically, we solve Einstein equations looking actually at a recipe that was actually cooked up by Albert Einstein a long time ago. And we actually solve Einstein equation assuming that the density profiles mimic were actually given by those that could represent dark matter profiles. Typical are for many models, you can actually represent them in a parametric way, and which depends on few parameters, it's gamma, beta, and alpha. For example, like for a particular choice of gamma, beta, and alpha, say 1 to 3, you get the usual Navarro-Franken-White profile or the Enquist profile, which are very, very common in people working on dark matter astrophysics. This is another class of models of profiles. But basically, what you do is that you solve Einstein equation with the stress energy tensor, which encodes this profile here, and you have your background solution. Now, if you want to study extreme and intermediate mass species spiral in vacuum GR in general, what you do is do relativistic perturbation theory, because you have a very little guy going around a massive object, so it's very, very natural to think about this problem in terms of a perturbative way, in which the perturbation parameter is the mass ratio. And indeed, if I have to basically solve the problem in vacuum GR, I will basically do this. I will basically compute perturbations around Schwarzschild or Kerr, and this perturbation here would actually be sourced by the particle, so the little guy going around the massive black hole. Okay. Now, I basically, instead of having a black hole, I'm more something like a star. Okay, because a black hole with some fluid around, and instead of perturbing only the metric, I also perturb the fluid. So I will basically have coupled to these perturbation of black hole velocity, density, and the pressure. Okay. How does it work? So I think you can draw a lot of interesting physical conclusion from this analysis, which still, I mean, it's a sort of toy model. And let's look first at the axial model. So basically, for Schwarzschild, you can easily split the perturbation induced by the particle into two families of modes, which basically depends on the parity properties of the perturbation, the axial and the polar. I don't know if you ever heard, but basically this leads in vacuum GR to what are called the Regge-Wheeler and Zerilli equation, which basically give you a solution for the perturbation. Okay, this is the easy one, which is the axial, and this is the equation that we get from a black hole embedded in dark matter. Now, the nice thing for axial modes is basically that this equation here, the functional form, is exactly the same as in vacuum general relativity. The only difference that we will get in vacuum GR is that this will be just the GDT component of Schwarzschild, and here you see an M of R, which is the mass of the space-time, that at infinity, basically, the IBM mass corresponds to the mass of the black hole and the mass of the halo, which for Schwarzschild would just be M, a constant value given by the mass of the black hole, and this guy here would be 0. Okay, but what is the wave equation for this would be exactly the same. Okay, and indeed, basically, if you look at the scattering potential, basically it's very, very close to vacuum. The only things that matters basically are difference given by the parameters of the dark matter halo, and in particular you see two parameters, remember this, which is the total mass of the halo and the scale of the halo, this A naught. Okay, take A naught as the typical size of the halo. Okay, now the thing that really matters when you do extreme mass species spiral are the fluxes. Okay, and because the fluxes the gravitational wave fluxes emitted by the binary basically drive the evolution of the system. And now, this is basically, this tells a very nice thing. And these are axial fluxes. And look first, basically, actually, this is the difference between the fluxes in vacuum and in matter. And this difference is just this solid contour here. Okay. You see difference which are of the order of, say, 0.1 and then 0.01. Now, in principle, you may believe that something which is of the order of 10 to minus 2, 10 to minus 3 is actually a small thing, a small relative difference with respect to the vacuum case or respect to your baseline model. But for extreme mass species spiral, I mean, the concept of small is not very clear, because if you take something which is 0.01, integrated over 10,000 orbits, this becomes basically a one effect that then can actually produce a detectable imprint. So in principle, this could actually matter. So the axial mode actually would carry a difference. But what you find is that there is something going on that actually makes axial fluxes at least less important of subdominant. Is that what we realize that this difference with respect to vacuum can actually be interpreted in terms of redshifted vacuum fluxes. Okay. So that basically, if you rescale the fluxes in terms of what we call the compactness of the halo, so the ratio between the mass and the typical scale, the relative difference decreases a lot, and then it becomes to a value that I can tell you is subdominant. Now, what is this redshift? This is really basically gravitational redshift, in the sense, before you have gravitational waves that were escaping at infinity from the black hole. Now you have that the potential well has deepened because you don't have only the mass of the black hole, but you also have the mass of all the spike that is there. So there is still the gravitational redshift, which is stretching the wave going infinity. And this basically is changing, at least at the linear order, the frequency and the fluxes.
But if you take into account these, basically the difference with respect to vacuum becomes almost abdominal. This is basically exactly the same effect that you would have in, I don't know, in constant gravitational waves. You never measure the pair masses. You always measure the detector masses, which are addressed by the redshift, which encodes the property of the distance, which basically tells you the distance of the source. Okay, you always measure a combination m times 1 plus theta. Okay, so you never know the actual pair mass. This is exactly the same at the linear order. Why this happens? This also happens because for axial modes, you don't get couplings between the fluid and the metric. Okay, so they are actually decoupled, but metric and fluid perturbation don't talk each other. Okay, so what you lose for axial modes is the coupling between fluids modes and the tensor mode, which I'm going to show you in the next slides. The situation indeed changes when you study polar fluxes. Now the situation gets a bit more complex, in that basically it took 1 year for us to solve this problem, because instead in vacuum GR you get a beautiful Zerilli equation, which is one equation, second order, and you can solve it with different methods. In the case of matter around, I mean, we're not able to find anything that reduces the problem to a sort of Zerilli-like problem. And so instead we have 5 equations that you have to integrate all together or couple, 3 for the usual metric. These 3 would become the Zerilli function if they were alone. Plus you have the velocity of the fluid and the density of the fluid that you have to integrate all together. And also pressure comes into the game here. So you have now 2 speed of sounds because you can get radial and tangential perturbation in your problem. Okay, long story short, this is again another plot showing now the polar flux, okay, which are actually even more important in general. And again, the blue, the solid actually, is the relative difference between the polar in vacuum and the polar in matter. And here, the dashed are again, this relative difference, if we try to interpret the fluxes as redshifted ones. And in this case, the redshift cure or fix is less effective, okay? And this is because together with a different background, so different background means that there is not only the mass of the black hole, but there is the mass of the halo. Now I have the coupling of the modes. I'll be more clear in a couple of slides later. But basically, I have these two and these two that talk each other, the exchange of energy. And so this exchange of energy cannot only be interpreted basically as redshift coming from the fact that I have a gravitational source with a different mass. And this actually can lead to detectable signature. Indeed, with Sarah, the PhD student at GSSR, we studied this. So once you have the fluxes, all of this is fully relativistic. This is an exact problem in its own way, okay? And there are no approximations. Basically, when you have the gravitational flux, you can study the evolution of the binary. So the evolution of the binary basically means you can study how the orbital phase and the radial distance of the binary changes. Okay, they will basically spiral, and you can compute in particular the dephasing, so the difference in phase that you would accumulate during this spiral if you try to interpret the signal with a vacuum template instead of with matter. Okay. The rule of thumb is that in principle the problem becomes interesting if this number here is larger than 1. I say rule of thumb because, I mean, even if you have 100 radians, I mean, the actual detectability of the effect depends on the parameter estimation, which means correlation of parameters and all other things. Okay? So, but this is a threshold for basically start saying, okay, this is really a problem that it would be interesting to look at, even from a phenomenological perspective. And here, basically, you see some cases. So this is a black hole of 10 to the 36 solar masses with an R of 10 to the 3 mass of the black hole. And basically, this, I don't even remember the label, but basically, this is the dephasing, okay, this is the mass of the secondary. So this is, for example, a 10 to 6 solar masses, which is coupled with a 10 solar mass black hole. So a stellar mass black hole of a 10 solar mass going around a supermassive black hole of 10 to 6 solar masses. And for two typical dark matter profile, this is the usual Navarro-Franken-White. And you see that basically you can accumulate some dephasing. And some of these can be of the order up to 1,000 of orbital radius that you lose in the spiral if you actually mismodel your waveform. So this tells you in principle, and actually this dephasing again is given by both these things, by redshift effect and by coupling between the modes in the gravitational and in the fluid part. So in principle, all of this is detectable. I don't know to the extent of this because we still haven't come to any sort of scheme to do this in a reliable way to throw in a Monte Carlo, but in principle it's a good sign.
So how far away are these orbits occurring with respect to the block?
10 M,
10.
more or less. I can tell you that 1 year of, yeah, now I remember actually. Indeed, the empty and the full boxes are 6 months and 1 year of observation. I can give you a typical value that's a 10 to 6, 10 binary. In 1 year, it is evolves from around 10 MP. All right, for the sake probably of time, I'll skip this. And I'll pass it through this, which is this spikes model actually allow us to study. I told you that what I actually wanted to give you is an overview of the possibilities and the observables that we actually can use. And one of these observables are the quasi-normal modes. Now, quasi-normal modes, these are the oscillations that actually the frequencies that characterize the response of a black hole to an external perturbation, and they are actually, since the 70s, they are known to be a probe of a dynamical probe of basically the black hole space-time. And what you actually can try to understand is whether quasi-normal modes can actually be used, even in this case, to infer the properties of the environment. And here, what we basically did with Peter, Francisco, and the others was exactly we took the model of the black hole blessed by the dark matter profile, and we tried to study the quasi-normal mode spectrum of these objects here. Okay. So again, what we did here was a time domain simulation in which we threw a Gaussian packet, a pulse as a perturbation to the black hole, and you try to see basically the response of the black hole. Now, I think this plot here basically tells you a bit what I was trying to tell you before about the coupling between gravitational and fluid modes. So this K is basically the metric perturbation that we get here. Okay. So this is the perturbation that you will get in any case, even if the black hole was in vacuum. And this instead is basically the density perturbation that is given by the dark matter fluid. Now, if you were in vacuum, of course, you will get only this. What we observed that basically if you compute, basically you study these and these, you can actually see that there is exchange, there is a coupling between these and these. So basically the two oscillating response talk each other and they exchange basically energy. And this is basically because of the couplings between the tensor and the fluid modes. So the gravitational and the fluid modes. So this is indeed, so yeah.
Well, my question, so I was trying to understand the model. So these are these spherical models where you have this
exactly the same
profile.
before, yeah.
But if I remember correctly, correct me if I'm wrong, then there's a violation of the dominant energy condition in these models close to the horizon. Is that true?
Yeah, the density actually dies before the horizon, and you can actually make the density small enough that basically the energy condition is not violated.
Yeah. Is it not violated or is it approximately?
No, it's not violated. You can make it.
That's all?
Yeah, yeah.
But you have matter, which is in between the, say, light ring and the horizon.
No, basically for this model, I mean, so we actually imposed an hard cutoff on this, but actually, if you study without even our models, like the peak that they basically is constructed this adiabatic growth, basically dies at 4M.
But then if it dies, you have what, a shell of matter? How do you solve the Einstein equations there? Is it a solution to the Einstein?
Yeah, yeah, absolutely.
But then if it just goes to zero, then there's a discontinuity in the derivatives. I mean, how do you solve? I mean, is it smooth?
It was not, yeah, so yeah.
But
For certain parameters, of course.
But it just
There is
goes
a
to
hierarchy.
zero there.
Yeah, we actually, okay, we solved
It cannot be C infinity yet.
okay, for this model, we actually put that the density F not cut off on.
Okay.
So
But then
you have to
there's
prescribe.
sort of a shell of matter there or something like that.
So you have to prescribe that at the density anyway. So it's,
And then you kill the area where you have violations of the dominant energy. That's fine.
yeah, again, yes, let's do this way. Yeah. Okay, so basically this is just to say that the fluid and the tensor mode talk each other, and basically there is the exchange that modulates the frequency content of the two. How these modes behave, and can we actually use them to constrain physics, the environment, the physics of the environment? The answer is no. Okay, And the answer is no, because I mean, we actually analyze them in several ways. These are just basically the relative difference between the frequencies of the real part component of the frequency of the quasi-normal mode that you will get in vacuum and for like this black hole spy matter. Okay. And I think the more important thing to notice here is that basically for small compactness, as those expected for like these dark matter spikes, still you get that this basically ratio is just controlled by the ratio. So basically what you get again is just a scaling of, now to be honest, this was only for axial modes, but it's basically just a scaling that depends on the ratio between the mass of the other scale, so say this is the compactness. So you really cannot tell anything because what you're going to measure is a different values that in principle without any probe you cannot really disentangle from this effect here. Okay. Again, these are dressed frequencies, not bare one. Okay. Vidor and collaborator actually have pushed a bit this thing to compute the effect on polar modes, so polar quasi-normal modes. And this is basically the time signal that you would expect at the end of the coalescence, after actually the coalescence. So this is the ring down signal, and basically there is a black line here that would basically correspond to a black hole ringing, so oscillating in vacuum, and then the other curves are basically ring down signals for dressed black holes with halos or spikes with different compactness here. Of course, I mean, if you push out the compactness, you see that the difference spikes up, and in particular, the part of the late part of the signal becomes increasingly more different from the vacuum case. Still, I have to say, these numbers are completely out of scale. You would expect in general that this compactness is much, much smaller than even 0.1, 0.01. So it was just a proxy to show probably the differences. But even if you use this value, basically you see that the detectability is extremely difficult. This is basically a plot showing that if you need to detect, so this is an extreme mass-rich spiral going around Sagittarius A star. If you want to measure the ring down oscillation of this black hole even with a compactness 10 to minus 4 of the halo, you would need an SNR of the order of 10 to 5, which basically is realistic. So it's very, very difficult. I mean, it's interesting to study them as a fundamental problem because, okay, you can gain insight on the couplings, the way they exchange energy, but it's going to be very, very difficult, at least with these models, that you can get some information.
Oh. And I guess it's a close one, right? So very like.
Yeah, here the actually, I don't even know, it doesn't. It's closer, but there's no distance here in the sense you can exchange the distance with the SNR. So basically, and in the sense that the source here, the distance is k such plus this particular SNR here, because the SNR goes as 1 over d. Okay, so you can basically translate this SNR. Basically, this tells you exactly that probably you need to have Sagittarius A star, I don't know, close to Pluto, something like that. Okay, I told you that in general for these massive particles, you would not expect the overdensities like to resist or to persist because of merger will actually disrupt them. But if you have ultralight dark matter, actually 2 weeks ago, like you presented something of related to this by Elvis group, and it was actually a series of work done by Pedro Ferrer and other people in 2022 and so on, in which basically they studied the orbital evolution of binary black hole in evolving in a scalar field environment. I think that the first, probably this work here was just made by the simple massive scalar field, so mu square by square with no self interaction, and they basically studied a bit the evolution of the system, and they found some interesting properties on where basically in which conditions the effect is more dominant or basically stays there and produces the largest dephasing. But I think that the real difference with respect to the previous case is that whatever the initial condition and the particular profile that shows for the initial condition, what they found is that after the merger, you still see that there is an overdensity. Okay, so it resists to this fashion unlike the massive particle case that I showed you before. And then basically this overdensity sits right, basically increased over the center, and then at the end you're left with a black hole after the coalescence with some overdensity around. What I was discussing with Carlos before, and actually what they did was also they analyzed different models, including basically self-interaction with lambda, and basically this parameter here controlling whether it was repulsive or attractive. And indeed, basically, depending on the particular sign of your self-interaction, it actually, in principle, this will actually be another way to constrain self-interaction, because the sign of lambda will actually increase or decrease lower, basically, the magnitude of the overdensity pair. Okay, repulsive interaction will actually flatten the overall overdensity at the end, so you will get basically that there's a smaller enhancement of the density in the spike, because the 5 to 4 term tends basically to flatten, to make the peaks shallower. Okay, I don't think that I have too much time, but for these objects, they actually keep their environment at least up to a certain point during the merger. It would be interesting to study if during the merger you can characterize the dynamical evolution of this dark matter, or in general the cloud profile. So let me explain better. In this work with Paolo and Rome and Valerio De Luca, we try basically to understand if you can get some information from this system here. So you have a comparable mass system, and this system here is dressed by an environment. This could be a scalar cloud, this could be a dark matter cloud in a lighter or not even too massive component here, something basically which deviates from vacuum. Okay. Now, this system here, like the one that we've seen in numerical simulation before, will actually be subject to tidal forces. So you would expect, basically, forgive about my representation here, that basically these things here would be tidally deformed during the spiral. Okay, and the tidal deformation that the clouds experience here actually depend on the particular the feature of the cloud component. This is basically very similar to what you would expect for neutron star, and actually this is what people use to study the neutron star equation of state. Binary neutron star basically get tidally deformed during the spiral, and the magnitude of this deformation includes properties, say, on the strong nuclear interactions, basically, that characterize the internal composition of the star. Okay. The difference with respect to neutron star is that in a binary neutron star match, you won't expect that basically the matter basically gets completely mass shed from the bag. I mean, there could be some mass shedding, but basically the star remains steady. It gets slightly deformed from its spherical distribution at the beginning, but it stays there. Here, what you would expect for environments that actually may completely disrupt, and indeed, like massive particles we've seen before, that you would get tidal forces that actually are so strong, and actually the environment is so diluted, that at the end, these get so tidally disrupted that you get just two naked black holes. And what we try to understand is whether you can actually model, even if an toy model, this kind of process. And what we did is basically use the theory of log numbers. So log numbers, I don't know if you ever heard, but these are super known just for binary neutron star in pure Python GR. These log numbers here is what I told you characterize the equation of state or internal composition of neutron star. Okay, take a neutron star made with quarks or with hadrons or with any form of matter you want. It will have different lambda. These enter the gravitational waveform, you measure this lambda, and in principle you can constrain the equation of state of dense matter. This is what actually Lagrange has done for GP 17087. What we did basically is use these, but dress the log number of a function that tells you that at some point the environment fades completely away. This is a toy model just trying to understand whether if you have an environment in which if you have a binary spiral in which the environment does not persist, still, basically, you can get some information on lambda and then on the properties of the density, or like the density of the environment. Okay, and these are basically the relative errors that we will get on all these parameters, because this function here is basically, at least in the model, the simple model that we characterize in this work, is basically parameterized in terms of few parameters. So the stationary log number, okay, actually static log number, this one, okay, which is independent of time, and then basically this function fcut and fslope that basically characterize the fact that this environment here at some point just fades away. And I mean, there are in principle some prospects. These are basically type of measurement that you could do with ice, depending on the masses of the binaries. Now I'm talking about comparable mass system with the Einstein telescope, and you can get actually, depending on the signal to noise ratio. Of course, louder is the signal, better is in general is the measurement, but basically you can get constraints on all the parameters of your feeding environment up to 110%. And these can actually be mapped to your specific model, because your the log number in general, again, as I told you, depend on the property of your environment. So for an Eurostar, it will depend on, say, the strong interaction that are inside the stellar core. If you take like a scalar field with some mass and B, the log number in some particular models, actually lambda is equal to K2. It's actually proportional to the gravitational coupling of your model here to some power of 8. So if I measure lambda or K, I can actually go back and constrain alpha and then B. And this basically shows you the constraints that we mapped from the previous values of lambda to the mass of the scalar field. So you see that basically you can get constraint up to 1%, depending of course on the gravitational coupling. And this is basically, this was a game that we played trying to understand. So if you say, I want a measurement of the mass of the boson through this model of the order of 10%, how far can I go to observe my system? And I mean, in some cases, you can really get a cosmological distance up to 10 giga. I'm done? Okay, I don't think that I have much more time, but I had probably 2 other cases. But okay, this is basically the take-home message slides that I want to show you. Is the environmental effects are there, and the thing that I really want to convey, probably, I mean, okay, even just with 2 models, the 3 models that we discussed, is that these environmental effects are active in a multitude of ways, and they affect the waveform, modifying the binding energy, the flux. There are additional dissipative channel, dynamical friction, like scalar radiation. There are the shifts in the quasi-normal modes, tidal response that changes in time. The problem is that for realistic densities, I mean, the majority of this effect is small, or can be, and actually can be treated as a small deviation from parametrically small deviation from generativity, which basically means that the reactivity is challenged. But there are some distinguishability signatures. Again, long phase evolution of extreme and intermediate mass spiral. It means that they pile up because these systems evolve for 1 year, 6 months, 2 years, 4 years in distance. So they have the time, and they also are very active in the frequency band where these effects are more pronounced. Actually, I didn't talk about, but I mean, there are other effects like resonances that could be actually even more. These are not parametrically connected to vacuum GR. These are more smoking gun signatures, probably difficult to model, but they are there. And there are, of course, the magnetic field couplings. Now, all of the things that I basically discussed about are toy models. Okay, I think the problem is that there is a lot of interest in this thing, but at the moment the majority of these are basically still investigation of fundamental astrophysics. The real problem is that if you want to do these things, especially try to catch up from the stream, the detector stream, something which is very, very small, you need faithful model. Okay, especially because think about the extreme mass spiral. If you talk with another data analyst, it tells you that if you have a template that you know how to model, it would be very, very good and important for parameter estimation to make a template accurate such that you don't lose, or you lose less than 1 radian in basically your evolution. Now, if you have a source with 100 radians, losing a radians is a challenge. If you have a source that complete 10 to 5 radians orbital cycles, 10 to 4, making a template such that you don't lose one of these becomes a bit more demanding. This is where basically Self-Force community, even just in vacuum GR, is fighting for the last, as fought for the last 3 decades. And so I guess that we can keep discussing about how all these things are super nice, but the real challenge probably now and in the future will be how to embed all of these in faithful templates that can actually be used to make fundamental physics searches. Okay, thanks a lot.
Thank you very much, Andrea, for the talk. So we can take one or two questions. It was very clear. But there was a discussion, but are there more?
I can just ask a question. So, I mean, you've given us a very nice overview of all of this and some possible distinguishable signatures. And in your opinion, what's the most promising?
I think probably something I haven't talked about. It's I don't know what is the so the dark matter spikes. I mean, I think it's interesting, but it's challenging. And I mean, there are all the models per se. I mean, have so many unknowns in the formation that it has been very nice so far doing like modeling of these in gravitational waves, black hole physics. But I mean, it's, the odds of having like the spikes there is not very very large. Ultralight fields, I don't know. I mean, it's could be, but it's personally something that I actually find very interesting are accretion disks. We know there are there for sure, and there is the challenge that basically can be extremely complex to model, and indeed we may come up with actually zero waveforms to do that. But there's an interesting thing that could actually be used to understand even without the like catching the real effect in the waveform, which is the multi-body interaction of an environment with a system. So if I have 1 minute, this is basically a work done by, actually Peter's work recently on this, but this work by the Milano group is very, very nice. So basically they have a three-body system, a massive black hole, and an intermediate mass black hole, and a stellar mass of black hole in a disk. Okay, these are these three circles here. So the massive black hole, and then you have the two small and smaller guys. Okay, and the fact is that the disk influences actually the evolution basically of the two. For example, and actually they influence each other. So basically there are perturbations induced basically by tidal force, by type 1 migration forces induced by the disk that force the two black holes to follow trajectory that they wouldn't follow if they were alone in vacuum. And then, depending on the property of the disk, basically you would have different basically outputs. So you have a three-body system, but you would have, depending on the strength, which basically means the density of the disk and the way it is formed, you could have, for example, an IMRI system. So basically intermediate and the stellar object that first merge. So these two merge as an intermediate mass-H spiral, then this produces a black hole, and then it merges here and in another intermediate mass-H spiral. This is basically an Emery, so the stellar mass guy first coupled to the big one, merge, and then you add the intermediate and now the final black hole like merge together. Or you can have an Emery, so first these two, big and medium, and then the merge together and this one. All of these bits, basically when you see at the stream of the signal, you will have like multiple signals coming because of the interaction of these. And the different outputs would actually depend on the fact that you have then disks with different viscosity or different properties. So I don't know an exact answer again, I think we're still in the avenue of exploring, but personally in the last period, and something that I'm more curious is like if you want to say this indirect signature of the fact that it's something, of course, something may be degenerate with tons of other things, but as actually the other effects that you will see in the wafers, to be honest. But this could be an interesting way, basically, also to see, also because it will be there. But to be honest, in general, accretion disk probably may offer like the previous view also because they would offer multi-messenger opportunities. So you could actually gain something because there could be like, and people have been explored abilities. The interaction of the binary with the medium could actually prompt some electromagnetic emission that you could in principle like target, and so like multi-messenger of this could actually have well, sharing degeneracies and disentangling particles. Accretion disk and forces probably. Drag forces.
Okay, thank you. Maybe is there any question online? Doesn't really look like it. So maybe just a short follow-up on that, but is there any maybe relationship or anything to learn or to talk about with people from protoplanetary disks, or I know.
Yeah, no. So I mean, basically, type 1 migration, and this is mediated by planetary astrophysics.
Okay.
I mean, in the last period, there have been works by, again, Francisco, also by Nico Younes groups, in which basically they have generalized in a relativistic setup, especially this kind of drag forces that talks about respective disk, but many of these come from planetary studies.
Well, we can continue the discussions over lunch, so
Thank
thanks
you
again, Andrea.
Very nice overview, Andrea. I'll just put things in my office that will be for. Okay.